In this section, I'd like to show you some applications of the differential equations. First one is the linear models. Population dynamics can be modeled by a simple differential equations as a dp over dt equals kp. P is the populations. The growth rate of the population is proportional to the population at that times. For example, we use the population dynamics to simulate the growth of bacteria. So this is separable differential equations. So we correct all the terms to the p into the left hand side and the k dt. Quite easily to integrate. Is the natural log p equal kt plus integration constant. Then p is expressed exponential kt plus c sub 1. So this is expressed c times exponential kt. So c is equal to the exponential c sub 1. Population is expressed c exponential kt with the two unknown constants c and k. So to determine these two unknown constants, we need two conditions. This is a linear models to simulate the growth rate of the populations. Now we introduce the nonlinear models. A linear model of population dynamics is too simplified. The growth rate of population is not always proportional to the populations. The maximum number of population could be determined by the limited source of food. A more realistic model of population dynamics was proposed by First around 1840s and is known as logistic models. So this is the logistic models. This factor of the a minus bp is really important. When the p is approaching to the a over b, what happens to the growth rate? This term is approaching to the 0, so dp dt is approaching to the 0. So p cannot increase over the a over b. Population cannot go beyond the upper limit of the determined by the a over b. So this is a better model of the population dynamics. So if you solve the practice, you will learn solution of the logistic models. Next topic is the systems of first order differential equations. Up to this point, we all consider the single dependent variables. But sometimes we might have two or more dependent variables. Then we have two or more equations to find the dependent variables. This is one of the examples, a predator-prey models. Two different species of animals, for example, rabbit as a prey and a fox as a predators, interact in the same ecosystem. Rabbits eat only vegetations, while foxes eat only rabbits. We express the fox and rabbit populations as x and y. So fox is x, rabbit is y. Then growth of the population is described by the following systems of first order differential equation. So we have two dependent variables, x and y. Independent variables is a t, times. Growth rate of the fox, dx over dt, is expressed without the food. The number of the foxes is decreasing. The first term simulate the decreasing rate of the fox. Fox can eat rabbit. So this is fox eat rabbit. Growth rate of the fox is dependent of the interaction between the fox and rabbit. So second terms simulate such a process. Fox eat rabbit. And the growth rate of the rabbit. This is rabbit of Y. Without the foxes, the number of the rabbit is increasing. So first term describes increase of the rabbit because rabbit only eat vegetation. We assume the vegetation always supplied to the rabbit. Second term is a fox eat rabbit terms. By solving these two equations, we could find the change of the populations of fox and rabbit. Number of rabbit and foxes can be simulated using these equations. When we consider the two or more dependent variables, we need to solve the systems of first-order differential equations. Okay, this is the end of the second chapters. So hope you learned how to solve the first-order differential equations.